in thinking of the applications of mathematics to physics, it's perfectly natural that mathematics will be useful when large numbers are involved in complex situations. And I would like immediately to say that mathematics has its primary application, it has a tremendous application in physics in the discussion of the detailed phenomena in complicated situations, granting the fundamental rules of the game. And that is something which, if I were talking only about the relation of mathematics and physics, I would spend most of my time discussing. But since this is part of a series of lectures on the character of physical law, I do not have the time to discuss the applications of mathematics and physics to calculating what happens in complicated situations, but we'll go immediately to another question, which is the character of the fundamental laws. If we go back to our checker game, the fundamental laws are the rules by which the checkers move. The mathematics may be applied in a complex situation to figure out what happens in the next move, what's a good move to make in a complicated situation, but very little mathematics is needed in the fundamental, simple character of the basic laws. Now, the strange thing about physics is that for the fundamental laws, we still need mathematics. For example, I give two examples, one in which we really do not and one in which we do. There's a law in physics called Faraday's law, which says that in an electrolysis, the amount of material which is deposited is proportional to the current and to the time that the current is acting. And that means that the amount of material is proportional to the charge which goes through the system. Sounds very mathematical. But what's actually happening is that electrons going through the wire each carry one charge. And to take an example, a particular example, it may be that to deposit one atom requires one electron to come. And so the number of atoms that are deposited is necessarily proportional to the number of electrons that flow, and thus to the charge that goes through the wire. So the mathematically appearing law has as its basis nothing very deep, requiring no real knowledge of mathematics. But it's not the kind of mathematics I'm talking about tonight. Now, if we take, on the other hand, Newton's law for gravitation, which has these aspects which I wrote down last time just to impress you with the speed at which mathematical symbols can carry information. We said that the force was proportional to the product of the masses of two objects and inversely is the square of the distance between them, and that bodies react to forces by changing their speeds or changing their motions in the direction of the force by amounts proportional to the force and inversely proportional to their masses. Now that's words, all right, and I didn't have to write the equation, but nevertheless it's kind of mathematical, and we would wonder, how can this be a fundamental law? How can this planet out there look, what does it do to it? It looks at the sun and it sees how far away it is, and it decides to calculate on its internal adding machine the inverse of the square of the distance, and that tells it how much to move. This is certainly no explanation of the machinery of gravitation. So you might want to look further, and various people have tried to look further. Newton was originally asked, it doesn't mean anything, it doesn't tell us anything. He says, it tells you how it moves. It should be enough I told you how it moves, not what. But people are often unsatisfied without a mechanism, and I would like to describe one theory which has been invented among others, of the type that you might want, that this is the result of large numbers. And that's why it's mathematical. And I give this theory, perhaps you've thought of it yourself. Every once in a while some student comes running in, he suddenly explains gravitation. Suppose that in the world, everywhere, there are flying through us at very high speed a lot of particles that come equally in all directions. They're just shooting by, and once in a while hit us in a bombardment. Then look what would happen. If the sun is here and the earth is here, then if the sun weren't here, there would be particles bombarding from all sides, giving little impulses by the rattle of these bang, bang, the few that hit, which would not shake the earth in any particular direction, because there is many coming from one side as the other, from top, from bottom. However, when the sun is here, the particles which are coming in this direction are partly absorbed by the sun because some of them hit the sun and don't go through. Therefore, the number that are coming from this direction toward the earth is less than the number that are coming from the other side, because here they have no opposition from no sun there. And it's easy to see, after some mental effort, that the further the sun is away, the less in proportion of all of the particles are being taken out of the possible directions in which particles can come. I mean, solar size appears smaller. And, in fact, inversely is the square of the distance. So there will therefore be an impulse toward the sun on the Earth that's inversely as the square of the distance, and is the result of large numbers of very simple operations, just hit one after the other from all directions. And therefore the strangeness of the mathematical relation will be very much reduced, because the fundamental operation is much simpler than calculating the inverse of the square of the distance. This machine does the calculating, these particles bouncing. Only trouble with it is that it doesn't work for other reasons. Every theory that you make up has to be analyzed against all the possible consequences and to see if it predicts anything else. And this predicts something else. If the Earth is moving this way, more particles will hit it from the front than from the back. If you're running in the rain, more rain hits you from in the front of the face than in the back of the head, because you're running into the rain. And so as the Earth is moving in this direction, it's running into the particles, rather, and running away from the ones that are chasing it from behind, so that more particles hit it from the front than from the back, and there would be a force also sideways whenever there was any motion. This sideways force would slow the Earth up in the orbit, and it certainly would not have lasted the at least 4 billion years that it has been going around the sun. So that's the end of that theory. Well, you say that was a good one, though. It got rid of the mathematics for a while. Maybe I can invent a better one. And maybe you can, because nobody knows the ultimate. But up to today, from the time of Newton, no one has invented another theoretical description of the mathematical machinery behind this law, and at the same time doesn't produce some wrong phenomenon. I mean, they have, like this model does it, but it produces something which isn't true. If this were the only law of this character, it would be interesting and rather annoying. But what turns out to be true is that the more we investigate and the more laws we find and the deeper we penetrate nature, this disease, that every one of our laws is a purely mathematical statement in rather complex and abstruse mathematics. This is relatively simple mathematics. It gets more and more abstruse and more difficult as mathematics. And why? I haven't the slightest idea why. It is only my purpose in this lecture to tell you about this fact. In other words, it's my purpose in this lecture to explain, really, why I cannot satisfy you, if you do not understand mathematics too well, in trying to explain nature in any other way. Mathematics is not just a language. Mathematics is a language plus reasoning. It's like a language plus logic. Mathematics is a tool for reasoning. It's, in fact, a big collection of the results of some person's careful thought and reasoning. By mathematics, it is possible to connect one statement to another. For instance, I can say that the force is directed toward the sun. I can also tell you, as I did before, that the planet moves so that if I draw a line from the sun to the planet and draw another one at some definite period, like 3 weeks later, the area that's swung out by the planet is exactly the same as it will be in the next 3 weeks and the next 3 weeks and so on as it goes around the sun. Now, I can explain both of those statements to you carefully, but I cannot explain why they're both the same. So that if you don't appreciate the mathematics, you cannot see. It may be unbelievable that I can demonstrate that equal times will be swept out if the forces are directed toward the sun. And just to, if I may try, I will show you one demonstration to show you that those two things really are equivalent. And so that you can appreciate that there's more to merely the statement of the two laws, that the two laws are connected such that reasoning alone will bring you from one to the other. And the mathematics is disorganized reasoning, and that it's good to know how to do that, so they will appreciate the beauty of the relationship of the statements. So I'm going to prove, if I may, the relationship that if the forces are directed toward the sun, that the equal areas are swept out in equal time. So we start, here's the sun, and we imagine that at a certain time, let's say the planet is here, and is moving in such a way that, let's say, 1 second later or 1 hour, pick any time, let's say 1 second later, it's moved in such a manner that it has gotten to the position 2. Now, if the sun did not exert any force on it, then by Galileo's principle, it would keep right on going in a straight line. So in the same interval of time, later, the next second, it'll move exactly the same distance in the same straight line to the position 3, were there no force. All right, now first we're going to show that if there's no force, equal areas are swept out in equal time. I remind you that the area of a triangle is half the base times the altitude, and that the altitude is the vertical distance to the base. And that if the triangle is sort of cockeyed, there's a name for it which I forget, obtuse, then the altitude is this vertical height here. See, I know about the triangles, I just don't know the name. Now let us draw the lines to these 2 points in the case that there was no motion whatsoever. The question, this doesn't draw very well, I'm not accurate, but these 2 distances are equal, remember. The question is, are these 2 areas equal? Well, consider the triangle made from the sun and the 2 points 1 and 2. It's this one. What's its area? It's this space multiplied by this height. And what about the other triangle, which is the triangle in motion from 2 to 3? It's this base times the same altitude. The 2 triangles have the same altitude and, as I indicated, the same base and have the same area. So far, so good. If there were no force from the sun, equal areas would be swept out in equal times. The 2 triangles have equal areas. But there is a force from the sun. And during this interval, from 1 to 2 to 3, the sun is pulling and changing the motion in various directions, this way, that way. To get a good approximation to that, we'll take the central position or average position here and say that the whole effect during this interval was to change the motion by some amount in this direction toward the sun. Because of the influence of the sun, the motion is altered by an amount that's poking in this direction. That's parallel to this, exactly parallel. These lines are parallel. It's the direction in which this new motion is. The new motion is a compound of what it wanted to do and the change that's been induced by the action of the sun. So it doesn't really end up at position 3, but rather at position 4. So now we would like to compare, it's getting complicated in the diagram, the triangle 2,4S and 2,3S. I'll show you that those are equal. Because they have the same base, those 2 triangles, this one here, and the one that happened when we had no force. The one with force and with no force have the same base. And do they have the same altitude? Sure, because they're included between parallel lines, and so they have the same altitude. And thus the area of the last triangle I drew is the same as the second one I drew, this 1, 2, 3, and that I had proved earlier was the same as the first one. So in the actual orbital motion of the planet, the area of the first, in second, and in the second are equal. So by reasoning, we can see a connection between the force, the fact that the force is toward the sun, and that the areas are equal. Not ingenious, no? Incidentally, Newton made his proof geometrical like this, and made all his proofs in his book geometrical of this type. Today we don't use that kind of reasoning. We use a kind of analytic reasoning with symbols, and I want only to show what it looks like in the notation of the more modern mathematics, where you don't do anything but write a lot of symbols to figure it out. First, we would like to talk about how fast the area changes, and we represent that by area dot. And the area changes because of when the radius is swinging, it's the component of velocity at right angles to the radius times the radius that tells how fast the area changes. So this is the component of the radial distance multiplied by the velocity or rate of change of the distance. Now the question is whether the rate of change of area itself changes. The principle is it's not supposed to change. The rate of change of area is not supposed to change. So we differentiate, so-called, this again, and that'll mean some little trick about putting dots in the right place. And that's all. You have to learn the tricks. It's just a series of rules that people have found out that are very powerful for such a thing. And this says the component of the velocity at right angles to the velocity. It is none. There is none. The velocity is in the same direction as itself. And the acceleration, which is this thing, the second derivative, or the derivative of velocity, is the force divided by the mass. So this says that the rate of change of the area is the component of force at right angles to the radius. But if the force is in the direction of the radius, as Newton said, then there's no force at right angles to the radius, and that means that the rate of change of area doesn't change. I just wanted to illustrate the different kinds of notation. Now, Newton knew how to do this, more or less. A slight different notation, but he wrote everything this way because he tried to make it possible for people to read his papers. He invented the calculus, which is this kind of mathematics, and is a good illustration of the relation of mathematics to physics. Mathematics, then, is a way of going from one set of statements to another. It's evidently useful in physics because we have all these different ways that we can speak of things, and it permits us to develop consequences and analyze the situations and change the laws in different ways and to connect all the various statements. So that, as a matter of fact, the total amount that a physicist knows is very little. He has only to remember the rules for getting from one place to another, and he's able to do it then. In other words, all of the various statements about equal times, the forces in a direction of the radius, and so on, are all interconnected by reasoning. Now an interesting question comes up. Is there some pattern to it? Is there a place to begin fundamental principles and deduce the whole works? Or is there some particular pattern or order in nature in which we can understand that these are more fundamental statements and these are more consequential statements? There are two kinds of ways of looking at mathematics, which for the purpose of this lecture I will call the Babylonian tradition and the Greek tradition. In Babylonian schools in mathematics, the student would learn something by doing a large number of examples until he caught on to the general rule. Also, a large amount of geometry, for example, was known. A lot of properties of circles, theorem of Pythagoras, for example, formulas for the areas of cubes and triangles and everything else. And some degree of argument was available to go from one thing to another. Tables of numerical quantities were available so that you could solve elaborate equations and so on. Everything was prepared for calculating things out. But Euclid discovered that there was a way in which all of the theorems of geometry could be ordered from a set of axioms that were particularly simple. And you're all familiar with that much geometry, I'm sure. But the Babylonian attitude was, if I make my way of talking what I call Babylonian mathematics, is that you know all these various theorems and many of the connections in between, but you've never really realized that it could all come up from a bunch of axioms. Modern mathematics, the most modern mathematics, concentrates on axioms and demonstrations within a very definite framework of conventions of what's acceptable and not acceptable as axioms. For example, in geometry, they take something like Euclid's axioms modified to be made more perfect and then to show the deduction of the system. So the first thing we have to worry about is that even in mathematics, you can start in different places. Because of all these various theorems are interconnected by reasoning, there isn't any real way to say, well, these on the bottom here are the bottom, and these are connected through logic. Because if you were told this one instead, or this one, you could also run the logic the other way if you weren't told that one, and work out that one. It's like a bridge with lots of members, and it's over-connected. If pieces have dropped out, you can reconnect it another way. The mathematical tradition of today is to start with some particular ones which are chosen by some kind of convention to be axioms and then to build up the structure from there. The Babylonian thing that I'm talking about, which I don't really not Babylonian, but it's to say, well, I happen to know this and I happen to know that and maybe I know that, and I work everything out from there. And tomorrow I forgot that this was true, but I remembered that this was true, and then I reconstruct it again, and so on. I'm never quite sure of where I'm supposed to begin and where I'm supposed to end. I just remember enough all the time so that as the memory fades and the pieces fall out, I put the thing back together again every day. The method of starting from the axioms is not efficient in obtaining the theorems. In working something out in geometry, you're not very efficient if each time you have to start back at the axioms. But if you have to remember a few things in the geometry, you can always get somewhere else. It's much more efficient. Now I would like to make a number of remarks on the relation of mathematics and physics, which are a little more general. The first is that the mathematicians only are dealing with the structure of the reasoning, and they do not really care about what they're talking. They don't even need to know what they're talking about, or as they themselves say, or whether what they say is true. Now I explain that. If you state the axioms, you say such and such is so, and such and such is so, and such is so, what then? Then the logic can be carried out without knowing what the such and such words mean. In other words, mathematicians prepare abstract reasoning that's ready to be used if you will only have a set of axioms about the real world. But the physicist has meaning to all the phrases. And there's a very important thing that a lot of people who study physics that come from mathematics don't appreciate. The physics is not mathematics, and mathematics is not physics. One helps the other. But you have to have some understanding of the connection of the words with the real world. It's necessary to, at the end, to translate what you figured out into English, into the world, into the blocks of copper and glass that you're going to do the experiments with to find out whether the consequences are true. And this is a problem which is not a problem of mathematics at all. I've already mentioned one other relationship that, of course, it's obvious how the mathematical reasonings which have been developed are of great power and use for physicists. On the other hand, sometimes a physicist's reasoning is useful for mathematicians. Mathematicians also like to make their reasoning as general as possible. If you say, I have a three-dimensional space, ordinary space, I want to talk about ordinary space. You know, you're in it and you measure distances and there are three numbers you need to tell where something is. You go breadth, width, and height, three-dimensional space, and you begin to ask them about theorems. Then they say, now look, if you had a space of n dimensions, then here are the theorems. Well, I say, yeah, but I only want the case 3. Well, substitute n equals 3. And then it turns out that very many of the complicated theorems they have are much simpler because it happens to be a special case. Now, the physicist is always interested in a special case. He's never interested in the general case. He's talking about something. And so there's a certain amount of reducing because the mathematicians have prepared these things for a wide range of problems, which is very useful. And when you know what it is you're talking about, that these things are forces, and these are masses, and this is inertia, and this is so on, then you can use an awful lot of common sense, seat-of-the-pants feeling about the world. You've seen various things. You know more or less how the phenomenon is going to behave. Well, the poor mathematician, he translates it into equations, and the symbols don't mean anything to him, and he has no guide but precise mathematical rigor and care in the argument. Whereas a physicist who knows more or less how the answer is going to come out can sort of guess part way and go right along rather rapidly. The mathematical rigor of great precision is not very useful in the physics, nor is the modern attitude in mathematics to look at axioms. The next point is the question of whether we should guess when we try to get a new law. The question is, to what extent models help? And it's a very interesting thing. Very often models help, and most physics teachers try to teach how to use these models and get a good physical feel for how things are going to work out. But the greatest discoveries, it always turns out, abstract away from the model. It never did any good. Maxwell's discovery of electrodynamics was first made with a lot of imaginary wheels and idlers and everything else in space. Dirac discovered the correct laws of quantum mechanics for relativity quantum mechanics simply by guessing the equation. And the method of guessing the equation seems to be a pretty effective way of guessing new laws. This shows, again, that mathematics is a deep way of expressing nature, and attempts to express nature in philosophical principles or in seat-of-the-pants mechanical feelings is not an efficient way. To summarize, I would use the words of Jeans, who said that the great architect seems to be a mathematician. And for you who don't know mathematics, it's really quite difficult to get a real feeling across up to the beauty, or the deepest beauty of nature. C.P. Snow talked about two cultures. I really think that those two cultures are people who do and people who do not have had this, people who have had and people who have not had this experience of understanding mathematics well enough to appreciate nature once. It's too bad that it has to be mathematics, and that mathematics for some people is hard. When it's reputed, I don't know if it's true, that when one of the kings was trying to learn geometry from Euclid, he complained that it was difficult. And Euclid said that there's no royal road to geometry. And there's no royal road. It's not we cannot, as people who look at this thing as a physicist, cannot convert this thing to any other language. You have, if you want to discuss nature, to learn about nature and to appreciate nature, it's necessary to find out the language that she speaks in. She offers her information only in one form. It seems to me that it's like all the intellectual arguments that you can make would not in any way, or very, very little, will communicate to deaf ears what music, the experience of music really is. And all the intellectual arguments in the world will not convince those of the other culture. We're talking to deaf ears. And it's perhaps that the horizons are limited, which permit such people to imagine that the center of the universe of interest is man. Thank you.